Okay, hi guys. So in this lecture, we'll be starting off with the application of isomerism. So let me start off by writing the heading. So application of isomerism. Okay. So in application of isomerism, we'll first see the reaction of alkene with HBr, H2, cold KMnO4 and Br2. Okay. So let's suppose we have a alkene, and this alkene is we are going to react it with some electrophile and some negatively charged atom on it. So it for the rate determining step would be the formation of carbocation here. Okay. So yeah, formation of carbocation is the rate determining step, and this will act as a nucleophile. Okay, and it's an exothermic path as more number of bonds are formed. So let us take another example wherein we need to calculate, where we need to find that which carbon atom would actually have the carbocation on itself. We have something like this, and we react it with HBr. We get something like in presence of CCl4. So either we can get a carbocation at this position, and or either we can get carbocation at this position. But this is actually the rate determining step, so we'll have to look into the stability of carbocation, and we can easily say that the carbocation formed in this intermediate is more stable than this one. Hence this would be not be the case, this would be the case. Okay, so now when actually we have already had an carbocation. Now the next step would be that the Br minus attacks on this carbocation. So the way in which Br minus can actually attack this carbocation is two. So it can either attack it from above the plane or below the plane. So now we have something like this, where we have this carbocation. I'm just taking this carbocation as it is. Now Br minus can actually attack above the plane or below the plane, from above the plane or from below the plane. So if it attacks, in both the cases we would have a racemic mixture in which this carbon will act as a chiral center, and we would have two compounds, in one in which Br is above the plane, and another one would be one in which Br is below the plane. So with this we get an racemic mixture, as these two compounds are enantiomers. And why it's a racemic mixture? Because it is having equal probability that the Br can attack from either above the plane or from below the plane. Hence it's a racemic mixture. We will get equimolar compounds of both the enantiomers. Okay, so let us take another example wherein we have this ring, and okay, this CH3, and let's have this double bond CH2. So now in this case, if we attack it with HBr, what will happen is this being a nucleophile will have a positive charge on this carbon. Now what will happen is Br minus can attack this chiral center either from above the plane or from below the plane. Okay, so in both the cases, if it attacks above the plane, Br will get above and CH3 will get lower. If it attacks below the plane, we will get CH3 as above the plane, and Br as it attacks below the plane, it will get it in dash. Okay, so both these two are racemic mixture. So are the racemic mixture? So actually I missed a thing. I'm sorry for that. We will if this was the case, uh, if this was the case, then what will happen is this example. So are the recipe mixture? No. Why? They are these two are identical only. So this will not be the case. Only this would be formed, and this is not a chiral center. Why? Because these two groups are same, hence it's a meso compound. Okay, but if we had something like in the previous example I wanted to show, but I'm showing it right now, that if we had something like this, then what will happen is positive charge will come on this carbon atom and CH3 will be formed here. Now Br minus will can attack this carbon atom from above the plane or from above the plane or from below the plane to form something like, if it attacks above the plane, Br would be here and CS3 would be here, and if it attacks below the plane, it would be something like CS3 here and Br here and CS3 here. Now these two are enantiomers, and as they are formed in equal proportion probabilistically, so they will be recipe mixture. Okay, so now let's take a look at another example wherein we have this and this. We are attacking with CCl4. So what will happen is the carbocation formation would be at secondary carbon because it is more stable. Now what happens is Br minus can either attack it above the plane or below the plane, forming a racemic mixture or not. No, it will not form a racemic mixture, it will form a meso compound. Why? Because it's not a chiral center, these two groups are same. Okay, so characteristics, let's talk about the characteristics of the reaction. Characteristics of reaction. So in this we would have characteristics would be, it is a electrophilic addition reaction. Okay, so electrophilic addition reaction. Okay, second point is formation of carbocation is the rate determining step, hence more stable the cation, more is the rate of reaction. So we'll just write it, formation of carbocation is rate determining step, more stable carbocation, higher is the rate of reaction. Okay, so let us now talk about rearrangement. So I just erased the previous board. So rearrangement. So rearrangement rearrangement takes place in these types of reaction. So with example I will try to explain you what type of rearrangement I am talking about. So let's say we had positive charge on this carbon atom. So what will happen is, as you know that this positive charge here on the secondary carbon would be more stable, so what will happen is 1 to H minus shift would happen, in which this H would leave as a minus group and will attach onto this carbon atom, forming a positive charge on the second carbon atom. So if we will have something like this. Okay, so as to increase the stability of compound of carbocation, stability increase of carbocation. Okay, second is something, if we have something like this, so what will happen in this case is, obviously we also know that on this carbon atom we would have more stability. So what will happen is we would have 1 to CH3 minus shift. So what will happen after the shift? This CH3 will leave as a CH3 minus group and will attach on this CH2 plus, forming a carbocation on this carbon atom. So CH3 C positive charge, CH3 CH2 CH3. This would be the result, and it's more stable than the previous one. Okay, so let's take some examples of the rearrangement before we move on to the next video. Some examples of this would be, so you have to identify the major product along with their stereochemistry. Okay, so we had something like this. This CH3 is coming out of the plane, and we have this CH2, and we reacted with HBr in presence of CCl4. Okay, so what will happen is, intermediate would be something like a positive charge here and a CH3 here. Okay, so one compound can be, after Br minus attacks this bond either from the above the plane or from the below the plane, so we would find something like this. If it Br attaches above the plane, then it would be something like this. If it attaches above below the plane, then it would be something like this. Okay, just draw a dash here and wedge here. Okay, so this is not an enantiomer, this is more of a diastereomer. Why? Because this CH3 was already above the plane. You are already given in the example itself, in the question itself. So this is a diastereomer. Okay, so we'll be taking on more of this type of examples in the next lecture. So till then, good luck and goodbye.